Hello everybody, we are Team EaglePicher and BATS Part 2, and this is our project on the Advanced Modular Battery System. Our technical directors for this project are Frank Puglia, the Director of Research and Development at EaglePicher, and Daniel Wertz, a Senior Level Systems Engineer also at EaglePicher. The designers that are working on this project include myself, Anissa Elias, a computer engineer, Christopher Sharon, an electrical and a computer engineer, Sean Thurber, an electrical engineer, and Nicholas Dort, an electrical engineer. With its headquarters in Joplin, Missouri, EaglePicher specializes in providing battery solutions for very demanding applications. They are a leading producer of state-of-the-art battery technology for aerospace, defense, aviation, and medical applications. Batteries that EaglePicher has produced have been used in many notable instances, such as providing the emergency power for Apollo 13, powering the International Space Station, powering the Mars rovers, commercial jets and helicopters, as well as life-saving medical implants and more than 85% of US missile platforms. Now, for the motivation of this project, it was to deliver the performance that EaglePicher customers demand and require. As it was said before, EaglePicher provides solutions for very demanding applications, therefore their batteries need to withstand the test of time and the harshest conditions. Having a battery management system with the ability to collect high-fidelity performance telemetry could prove invaluable in evaluating battery cell design. Illuminating the unique characteristics of candidate battery cells will aid in establishing the minimum requirements for a deliverable BMS design. Ultimately, a better understanding of cell characteristics and how those characteristics can be observed and interpreted by the BMS is the next step in optimizing the use of the batteries in both first and second life applications. Team MBATS's anticipated best outcome was split into two parts. First, we will be creating a battery testing system that will measure all parameters of our battery pack. That battery pack is made out of 12 18650 lithium-ion cells, all connected in series. Each individual cell's parameters, which include voltage, current, temperature, resistance, state of charge, state of health, will be measured, and they will be measured using a battery management system and a real-time data acquisition system. For the second part of our anticipated best outcome, it will be taking that data collected, synchronizing, filtering it, and then using it to create predictive models using machine learning algorithms to predict the state of a cell and the damage it might withstand under certain conditions. But to be able to create that best possible testing system, our team had to build up an extensive background in battery chemistry and battery behavior. This simply began with understanding what battery parameters were important, how each parameter would affect the battery performance, and what would be the best possible way to collect these parameters. After understanding all of the background information, we moved on to choosing the key components in our system, the battery management system and the real-time data acquisition system. We had multiple options for both, but ultimately, after many weeks of research, we concluded that the Orion BMS would be our best choice as it is the most popular between consumers and it represents the current commercial off-the-shelf BMS solutions the best. As for our DAC system, we chose two National Instruments N9202 voltage measurement modules that will be used to measure voltage, temperature, and current of our 12 cells. But to be able to use and collect real raw data from the DAC, the team had to design signal conditioning circuits to output voltage in a readable range and for the current sensor to operate. A buffer amplifier and a voltage divider circuit were also designed for our DAC temperature readings, and lastly, a programmable load circuit was designed to be used while running discharging tests on our battery pack. And after creating this overall system, we decided, with the help of our technical directors, that having a 4-layer PCB to host all the wirings from our BMS and DAC to our batteries will be the best possible way for our test fixture to be designed. And after that, with all of our technical and electrical components chosen, our test fixture designed, approved, and just waiting for the PCB to be printed and shipped to us, we moved on to our data collection, machine learning algorithms, and predictive models. As the data we will be receiving from the DAC will be raw data, we created a conversion sheet that will allow us to output some parameters such as state of charge and state of health easily from the DAC to match the BMS. And our last accomplishment this semester was one that would set us up for success in the upcoming spring semester. With the help of our technical director, Frank Puglia, we were able to create a graphical user interface that allows us to input certain characteristics of cells, run certain tests on them, and then the output will clue us on which cell had the best outcome and what characteristics will be the most useful to withstand certain conditions. This product that we are creating would set EaglePicher up to be able to advance their studies in the usefulness of worn batteries and what they can be used for after their primary use has been exhausted. The technology would be capable of being mass-produced and be capable of detecting damaged and malfunctioning battery cells that otherwise would not be able to be diagnosed in the field. By optimizing the BMS around the most important parameters to measure for both safety and state of health and charge, EaglePicher Technologies will set the standards for providing rapid solutions for critical applications. Now for a more in-depth discussion of our technical accomplishments, and with the majority of the semester's progress being focused on choosing and assembling the best data collection system we could possibly create, I individually focused on making our next semester tasks clearer. With the help of our technical director, Frank Puglia, a fake battery dataset was created and utilized to allow us to get an understanding of battery behaviors under all sorts of conditions. I created a graphical user interface using Python's tkinter library that would allow a user to define the desired characteristics of their battery pack. Then, that user has a choice of calculating one of 7 outcomes that would either be outputted in a CSV file or another window of the interface. Currently, we are at a point where the user is just receiving an instant response for one test at a time, but a continuous testing cycle where test n would affect test n plus 1 is being implemented at the moment. The implementation has required artificial intelligence methods that would understand when to stop testing, or in a more physical sense, to stop using the batteries once a certain cell has endured too much damage to operate on the same level as all of the other cells. In a real-world setting, this is where an operator would be alerted by the system we're creating that a cell is experiencing failure to operate. With this data being very useful, I have started to create how a profile for certain cells should look like in terms of damage endured, and these profiles will be utilized later on to indicate which parameters should be optimized to minimize overall and individual damage of cells. This is how the interface looks like, where a user is able to input the characteristics that they would like their batteries to have, and the choices they have to calculate is overall damage, voltage response, voltage damage, cell temperature, temperature penalty factor, entropy penalty, and pack voltage. This is an example of how the interface is being used, where I had a basic battery profile provided by our technical director, and I wanted to calculate the overall damage, where this would pop up in another window of the interface and give me the average damage, max damage, and some other useful information for each of my cells. And now, as we move towards the new semester, what I plan on doing before April 15th of the new year is to first assemble the test fixture with the rest of the team and finally begin collecting our data. In the beginning of February, I would like to also be done with creating the profiles that come with our fake data in the user interface I've created. I would then begin synchronizing and filtering the DAC and BMS data, and then that should set us up to begin creating our predictive models by March, and by the middle of April, I hope that I've created battery predictive models that work after being extensively tested. And now, to our next designer, Sharon, who will tell us about the voltage divider circuit and the PCB design.
My focus this semester was on creating the test fixture that will allow for the collection of data used in our predictive models. We are only using voltage modules for our data acquisition unit, and one of the challenges of doing so is that signal conditioning is needed to allow measurement from our sensors. This circuit is a voltage divider that allows for temperature measurement from the thermistor sensors. Based on the characteristics of the thermistors and the components used in the circuit, I was able to define a formula that will provide the temperature of the thermistors by reading the voltage across them. The thermistor voltage divider is located on what we have dubbed the battery board, and the schematic and layout are shown here. This board was designed with the goal of collecting the information needed from the battery cells and outputting it to the appropriate DAC and BMS ports. This board will route the proper temperature and cell voltage measurements and allow connection from the battery cells to the load and charging circuits. Containing all of these connections within a PCB has the added benefit of creating a much neater fixture and allows for an effortless setup. Here's what the board will look like. As the cell holders are mounted directly to the board, we also have the ability to interchange entire battery groups without having to remove individual cells. With this board, we are one step closer to finishing our test fixture. The accomplishments I want to make before April 15th of next year will first be refining the battery board design and completing the test fixture. After completing the test fixture, we will begin to collect data, and I plan on finishing the synchronization of the data between the DAC and the BMS by early February. The next and final step to achieving our ABO is to create and test the predictive models for our batteries. Our next designer is Sharon, who will tell us about our analog load circuit and current sensor signal conditioning.
Signal conditioning is needed for the National Instruments DAC modules chosen to read current drawn from the battery pack. The current sensor chosen is the LEM LA205S. It has a 1 to 2000 conversion ratio and requires an external resistor to set a voltage scale to represent the current passing through. The formula shown will provide the current as a 10-volt scale for 10 amps with a 50% margin. Moving on to the programmable load profile circuit, the aim is to create a dynamic discharge profile from the battery pack ranging from 0 to 10 amps. This is an expansion on the initial draft and calculations provided by Dan Wertz with a usage profile provided by Frank Puglia. A logic driver is used to control a clamping circuit, which would drop the gate voltage of the transistor connected to the bulk resistor, thus closing the load channel. With 8 channels, an 8-bit digital signal is used to switch on or off each individual channel, which would allow for 256 steps between 0 and 10.24 amps. With a reference voltage of 100 millivolts, resistor values are calculated to match this voltage on the negative feedback of each channel. These resistor values were adjusted for standard values, and a variable trim resistor provides fine adjustments. Power dissipation is calculated to ensure components purchased can handle the power through them. A simulation was performed in Multisim with non-ideal components. Earlier simulations had transient current spikes at the edge of each load change, which are now gone. However, the maximum current drawn on the highest channel is around 4.35 amps, below the 5.12 amps expected. This could partially be due to models chosen for non-ideal components, but the issue remains as of now. Due to the recent acquisition of an electronic load supply, this load profile circuit has been repurposed as a backup plan. While inherent limitations in an electronic load supply limit the type of load profiles we can apply, the focus is currently on getting a test fixture to start collecting data. The accomplishments I want to make before April 15th include finalizing the remaining signal conditioning and wiring the physical test fixture. After this, I will assist in collecting data from the discharge cycles and synchronizing data between the BMS and DAC. And provided enough time, I would also like to finish the analog load profile circuit, as this would prove useful for future continuations of this project. Another important factor of our battery testing platform is the physical layout, with the ability to easily swap out one battery pack for another for rapid testing. Responsible for this is Nicholas Duarte.
Hello there, my name is Nicholas Duarte, and I'm going to share with you some of the accomplishments that I've personally made with this capstone project over the past few months. The first couple of slides are models of the hot swappable tray that are going to be housing the PCB that Chris has been working on. These parts are going to be 3D printed. We're going to make 2 of them to house 2 separate stacks that we'll be working with. This slide shows how we plan on securing the PCB to the tray through press fit screws. So it'll be raised off of the 3D printed surface. This slide is a depiction of how we think the final rig is going to look. As you can see, the PCB is going to be centrally located for easy cable management and ease of removal, so we can swap them out. Next semester, while Anissa and Chris are working on the AI to make sense of all the data we are collecting, it's going to fall to Sean and myself to put together all the hardware on the base and design a variable load circuit to test the discharge rate of the cells. To wrap up this presentation, our future goals and technical accomplishment goals are going to include signal conditioning and data collection, as well as designing a machine learning algorithm so that the AI can give us critical information about battery cell life and possible defects. I'd like to acknowledge our technical directors, Dan Wertz and Frank Puglia, for giving us guidance on this project, as well as Dr. Sunak for giving us the opportunity to make such a big impact in this field. We would also like to give a very special thanks to Dr. Zhang for giving us space in his lab and letting us use his equipment. Without his help, we would be hopelessly over budget. I want to thank you all very much for listening. Have a great day.